Now, are you seeing my screen?
Yes, clearly
It is
visible.
in full screen mode?
Yes, it's in full
Okay.
screen.
Thank you. Thank you. Okay, so yes, I am from Nicholas Copernicus University. It is a small city in Torun, Poland. And can you see my pointer?
Yes, yes, yes.
Okay. So this is our university, and this university is basically in Torun. Torun is a small city in Poland, roughly 3 hours from the capital Warsaw. Torun is situated in the beside of the Vistula River. Most importantly, Torun was the birthplace of the very early scientist, a great mind of Nicholas Copernicus. So, with this introduction, I would like to begin my talk. I am a computational chemist, as introduced by Dr. Sardar. So, in contrast to the previous speakers, Professor Hajra and Professor Banerjee, I'll bring some different perspective to this symposium. So, I do chemistry in a computer instead of laboratory, right? So first, let me establish some connection between the so-called green chemistry and the computational chemistry. So computational chemistry is there are a few features of computational chemistry. Very easy to perform, of course, very safe to perform, less expensive than real experiments because you don't need chemicals, which is expensive. You don't need to use a lot of instruments, which is also expensive. And as you can understand, there you don't have any safety issue. I can test my theories in a wide variety of molecular systems, right? I do not need to care to synthesize this molecule. I do not need to care that, okay, how stable is my molecule is, or it is unstable. So basically, I can test my theories, my computations in a wide variety of molecular systems, any molecular systems that I want, and then I rationalize and I try to explore the inside chemistry, what is happening. Maybe this inside chemistry, what is happening behind our experiment. This is the main goal of computational chemistry: to explore, to rationalize, and to understand the chemistry beneath our eyes. And as you can see, there is no chemical hazards. So basically, we would like to think this also a green chemistry approach, but since we are not doing experiments, people came up with a different terminology. We call it in silico chemistry. Why in silico? Because of course you can understand it is doing in computers are made of silicon chips at that day, so that is why people give this fancy term in silico chemistry. So nowadays computational chemistry and in silico chemistry kind of synonymous. But all these easy things are not coming without a cost, right? There is no free lunch. So the main bottleneck of doing computational chemistry is the accurate formulation of the theory. And I can explain you in a bit slowly what do I mean by theory. And then nowadays we have a zoo of methods, right? You all know DFT, CAS-SCF, CAS-PT2, NEP-PT2, a lot of even molecular mechanics, QM, quantum mechanics, molecular mechanics, hybrid methods. So within this zoo of method, we need to choose our proper methods that describe my system well. And the last Difficult part is to develop a complete protocol that we call the method development, that is to build the software. So these are the main three pillars of computational chemistry. So yes, computational chemistry can nowadays is much advanced, predict molecular structures. You can put any molecule in your favorite quantum chemistry codes and ask for ionization potential, electron affinity, binding energy, barrier heights. Most of the cases, if you not do anything horribly wrong, you will get satisfactory results, either in DFT, either in any web function based methods. You will have molecular properties. The most important thing, you will have the electron densities. And by these electron densities, experimentalists now design that, okay, where you can probe your molecule for any other reactants to attack. I mean, electrophilic attack, nucleophilic attack. You can think that, okay, here is the electron density looks like this for this molecule, so I should prepare another reactant to attack from that part of the region, whatever you like. And then you will have, you can also predict absorption spectra, emission spectra, what experimentalists measure regularly. And then you can validate your theory that, okay, your theory is working right. Now the next work begins, that is to explain the chemistry. If you do dynamics, then you will collect all your molecular snapshots as a function of time and prepare a molecular movie. And you can see that how your molecule is doing during the reaction. And by another statistical theory, you can also predict reaction rates and a lot of other things too. So as you can see, Paul Dirac said that, okay, we know now the electrons. So a lot of physics and the whole part of chemistry is understood. The laws are more or less understood well, but to apply them in our real molecule is the main difficulty, because there is no exact solution. There is exact solution, but you cannot solve it. It is so mammoth, it is so huge. So you need a computer to solve it. Still, you cannot solve the exact solution. You have to put a lot of approximation, good approximations, and then you need to solve your molecules, your molecular systems in an approximated way. And if your approximations are legitimate, then you will get a good answer. Talking about the approximations, more or less, computational chemistry works in these three main pillars. One is molecular mechanics. Molecular mechanics is simple classical physics, right? So by classical physics, you calculate force fields. What does it mean? The mean is your atoms, you simulate your atoms as spheres, bond as springs, and you can ignore the electrons. So there is mainly classical mechanics, Newtonian mechanics is going on in your model, and you have Hooke's law for the bonds and collision theory for atoms. It is very inexpensive in the sense computationally cheap, and you can get semi-qualitative answer. Then people came up with the quantum mechanics, right? And of course, you have to solve Schrodinger wave equation. As you can know, as you can see, now it will be very costly because you have an arrangement of electrons and the the interaction of electrons with the nuclei. That is the main difficult part, the correlation energy between the electrons. But it is accurate if you can do it, and of course, very expensive. So always we have to think, we have to balance between these very costly and less costly methods. So people came up with hybrid QMMM methods. So in this type of hybrid quantum mechanics, molecular mechanics method, Now you have a system of interest. Now you have a system of interest which is shaded in red region, which you want to solve via quantum mechanically. That means by solving Schrodinger equation. And the other part, maybe they are solvent or some other part of a big protein. You are solving them via molecular mechanics. Again, via classical physics. And you have to determine the interaction between the molecular mechanics and classical and quantum mechanics in these region, the dashed white regions. We call them interface region, interface between molecular mechanics and quantum mechanics. But more or less, the idea is like this, that you have a quantum mechanical region, you have a molecular mechanical region, and you solve it via an approximated way. I am interested in light matter interactions. I am interested in photochemistry. And by saying photochemistry, what do I mean? I mean, when I am interested in a system after absorbing light. So photochemistry concerns the absorption, excitation, and emission of photons by atomic and molecular systems, right? So what happens when a molecule absorbs light? As you can see in this classic example of a steel beam, there is a two photoisomer, one is a cis and one is trans. So if you do not have light, you cannot convert cis to trans or vice versa because you have a large barrier height. But when you shine a light on the either way, cis or trans, then your molecule is promoted to the higher excited electronic states, and then it comes down, and now the barrier height is no longer seen by the molecule from the excited states, and it can come down here or here. So basically, photoisomerization is much more effective for this steel beam case. For this isomerization, the photoactivation is much more effective. So this interaction with radiation, that means light, with your molecule, requires a physical and chemical changes. So how it works? Let me first tell you how it works theoretically. So in the ground state, you are happy with your nuclei and electrons are in equilibrium like this. Then you shine a light. Immediately, the light changes the electron clouds of your molecule, the electronic distribution. And nuclei and electrons are not in equilibrium now anymore. So with this changing electronic cloud, now your nuclei has to respond. So your nuclei are now rearranged in another manner, in a different manner, to respond with your changed electronic cloud. And then with this changed nuclear configuration, then again your electron clouds are changed. So basically, this is the light matter interaction. We start from this configuration, and during the light interaction, we came to this configuration, a completely different configuration. This is a complete photophysics or photochemistry theory, can be schematically said. Okay. So with this light matter interaction, the classic example of light matter interaction, of course, you know, photosynthesis, vision process, solar cells. Within these solar cells brackets, previous speakers were saying photocatalysis. We have a lot of photocatalysis with metals. They are now effective, and people in Europe, I'm seeing a lot of solar cells are generated already, installed already. I know in India also solar cells are working very good. We have photoelectronics, nowadays we are having beautiful screens and we watching our movies very comfortably. It is because of the LED and OLED screens. And also people are now trying to cure cancer by this photodynamic cancer therapy. If I can add to this photodynamic cancer therapy, what is going on? It in US. It is very much nowadays people are. It is clinically proven and it is effective in your in treatment of your skin cancer. So basically, people are injecting, doctors are injecting some kind of sensitizers. It is completely organic, no metal is there, to your blood and try to attach these sensitizers to your DNA. And then they shine some light. This light effectively promote the photosensitizer to the higher electronic ground state, as you can see here in steel beam. And then this photo-excited sensitizer will come down to a triplet state. Triplet state is highly energetic and it reacts with oxygen present in your cells and produce reactive oxygen species. This reactive oxygen species actually reacts with your cancer cells and make them die. So this is the basic underlying of photodynamic cancer therapy. There is a lot of arguments, there is a lot of research going on, but we are still not at the very 100% success rate, but we are also trying to develop good photosensitizers to have effective photodynamic cancer therapy. Okay, so now the basic, now the theoretical foundation of photochemistry. So whenever we talk about this photochemistry, actually we are trying to simulate something about this picture. So this is your molecule in the ground state, as you can see. After absorbing your light, as I said, your molecule is promoted to higher excited electronic state. And then your molecule can be converted to another excited states, come down to another excited states. If it is the same spin multiplicity, we call it internal conversion. If it is the other excited state is different spin multiplicity, let's say singlet to triplet, we call them intersystem crossing. And then finally, from the singlet to singlet fluorescence happening, and from triplet to singlet, final relaxation is happening via phosphorescence. So here, actually, when we try to simulate this, actually we are trying to model the time evolution of the nuclear wave packet through a manifold of electronic states. And as you can understand, now your favorite Born-Oppenheimer approximation that you read in your master's textbook is now failing, because now you cannot decouple your electronic and nuclear motion. What is Born-Oppenheimer approximation? Born-Oppenheimer said that nuclear are much heavier, so it moves very slowly compared to electrons, so we can decouple the motion. But now in this excited states region, when all the excited states are approaching with each other, you cannot decouple the electronic and nuclear motion. So a new area emerged that is called non-adiabatic regime. And if we take a look at the time scale of these non-adiabatic transitions, it can range to femtosecond to nanoseconds even. Okay, the good news is nowadays we have an arsenal of methods capturing these wave packet bifurcation, capturing these time evolution of the nuclear wave packet through different electronic states. If you like quantum dynamics, we all like, then you have MCDTH based method. These are different names. I am not going to tell these details because it will require another 2 hours. But I'm just throwing you some names to get you familiarized. So you have grid-based quantum dynamics like MCDTH and the multi-layer version of MCDTH. You can do this, but the problem is it is very costly again because it is fully quantum, and because of this cost, you cannot model your molecules effectively. That means after 6 to 8 dimension, you cannot do a proper quantum dynamics. You need to put a lot of approximation, and then you do your quantum dynamics. We also have these trajectory guided quantum dynamics developed by Todd Martinez in the Stanford University. We call it multiple spawning. Basically, these trajectories are propagating classically, but the nuclear wave packet is constructing, again solving quantum dynamics, again solving time-dependent Schrodinger equation. So that is why it is called trajectory-guided quantum dynamics. Then people go on with further approximation, and then in a classical limit, people are having mixed quantum classical dynamics like trajectory surface hopping. I will tell a little bit about trajectory surface hopping because this is my method. And this trajectory surface hopping, we normally propagate all our trajectory simply classically, but the force is derived by solving time-independent Schrodinger equation. I will tell you in a bit. But the obvious question is arise: how well the methods are doing right now? Right? We have I have shown you.
Please switch off your audio. Oyon Bandyopadhyay, please off your audio.
Okay. So the obvious, I have shown you. I have thrown some names of dynamical methods. The obvious question is how well the methods are doing, right? Interestingly, Journal of Chemical Physics this year proposed a prediction challenge of cyclobutanone photochemistry. What is this? So a gas sample of cyclobutanone will be irradiated, a gas sample.
Off your audio.
Okay. So in this prediction challenge, JCP said, Journal of Chemical Physics said that in an experiment, it is a double-blind experiment, a double-blind challenge. The experiment will be happening in Stanford. The gas sample of cyclobutanone will be shining with this 200 nanometer of UV light. Now we know that the molecule will be promoted to the S2 electronic state, that is a Rydberg state. And then JCP told us, so this is the experimental setup JCP told us. Us means the photochemistry, we those who are doing photochemistry, and then across the world, all over the world. Then we have to simulate, we have to predict what will happen in the experiment. So we all submit our results. There are now 20 theoretical predictions in this JCP publication, but still we are waiting for the experimental results. Then we will know that whose methods are doing good or whose methods is not working at all in this scenario. So this is a nice thing to advertise. Okay, so this is actually, this slide is from that paper. So this is the cyclobutanone. We track the time evolution of the population. You can see that you can say that this is the population change as a function of time. So initially it was in the S2 state, and then it comes down to S1, and then finally it relaxes to the ground state. in a time scale of 9 picosecond. And then we collect all the geometries through the dynamics and prepare these electron diffraction patterns, what they will collect also in the experiment. Now we are waiting for the experiments. Okay. But all I am talking about, all I'm talking so far is non-adiabatic dynamics, non-adiabatic simulation in the ultra-fast time scale. And we believe that nowadays, till now, non-adiabatic simulation is biased towards ultra-fast time scale. That means up to a few picoseconds. And it is well reason to do that because it is very costly. If I say that, okay, I need to simulate a 1 picosecond dynamics of let's say a medium-sized molecule, right, pyridine, it will require 1,100 CPU hours. You can calculate this in a very simple mathematics. If you have your number of trajectories multiplied by the physical process you want to go, let's say 1 picosecond, that means 1,000 femtosecond, and this is your time step. And one single point calculation, if one single point calculation requires half CPU hour, that means 30 minutes of CPU hour. If you do, let's say, TDDFT of pyridine, in a big functional, you can spend 30 minutes for a single point, then you will have 1,100 hours of CPU hour. Now in France, we normally buy CPU hours in the rate of 0.02 euro. So this simulation, only this pyridine simulation will cost 2,000 euros. And the minimum wage in France in 2024 is 1,700 euros. Not only that, your simulation would have a carbon footprint of 65 kg, equivalent to 6 tree years. That means here we are not looking at neither a very economically friendly simulation nor a environment friendly simulation. So we need to think something beyond. And that is the next challenge in computational photochemistry, that is simulating non-adiabatic photodynamics in long time scale with reasonable. You cannot spend 1 year or 2 years for simulating one single molecule. So I define my long time scale by these two criteria. One is physicochemical criteria, where the phenomena is taking much longer than 10 picosecond. Why? Because nowadays it is currently doable. 10 picosecond dynamics I can do. So I am really pushing the boundaries of current capabilities. And in technical terms, if my simulation requires more than 10 to the power 5 integration steps, then I will call that, okay, this is my long time scale. Integration step meaning actually what we are doing. We are solving either time-dependent Schrodinger equation or classical Newtonian equation. If you know, both are actually differential equation. That means we have to solve it via integration. So these are the integration steps. I ask the same question again, that okay, how well the current methods are doing in the long time scale. So here I will compare those methods, MCDTH, that is quantum, trajectory guided quantum dynamics, that is multiple spawning, and fewest switch surface hopping, that is mixed quantum classical. So I simulate all these methods in a spin boson model Hamiltonian. What is spin boson model Hamiltonian? It is not a real molecule. It is a model Hamiltonian, two-state. We have two electronic states, and I prepare it 10-dimensional way. And we are seeing that more or less all the methods within the error of margin are predicting satisfactory results. That means in the red, I am seeing all the quantum dynamics, the lifetime is more or less 7 to 8 picosecond. In the blues, this is the multi-layer version of MCDTH. Again, the time scale is 7 to 8. The AIMS is green, AIMS meaning the trajectory guided quantum dynamics. Is green. It is slightly low lifetime because this is not the normal AIMS. It is a highly crudely approximated AIMS. Why? Because if I want to do the normal AIMS, my computer will explode. So I had to kill a lot of basis functions to propagate my trajectories. And probably that is why the lifetime is much slow here. And in the brown, you are seeing the surface hopping, which is the upper bound, of course, because surface hopping is very ad hoc theory. But if you now see the time as the last column, okay, quantum dynamics is good, but of course costly. AIMS is doable, but at least in this version of AIMS is crudely approximated. So at the end of the day, we have fierce switch surface hopping. It is reasonable and cheap. So I will propose the surface hopping is a reasonable method for long time scale dynamics. Let's understand how this non-adiabatic mixed quantum classical dynamics, that is surface hopping, is working. So first, you split your systems into two subsystems, right? One is slow and one is fast particles, like electrons and nucleus. So slow particles, that is nuclei, you follow classical trajectories. For the fast particles, that is the electrons, you solve them by solving time-independent Schrödinger equation of motion. It is nothing but solving a quantum chemistry calculation. You ask your favorite software, hey Gaussian, please calculate energies and blah and blah and blah. Gaussian will give you. This is the time-independent Schrödinger equation calculation. And then a non-adiabatic algorithm, this is the main crucial part, actually binds these classical Newtonian equation of motion and quantum mechanical equation of motion, ensures the self-consistency of both the subsystems. This is the basic philosophical idea given by long back 1998 Tully, by Tully from Yale University. So in the trajectory surface hopping, as I said, I propagate a swarm of independent classical trajectories on a single potential energy surface via Newtonian mechanics, right? And then at each point of my nuclear coordinates, I ask my favorite software, hey Gaussian, hey Turbomole, hey MolPro, please give me the electronic energies, the gradients, and the non-adiabatic coupling vector. It will give me those, and then I allow the trajectory to change between surfaces. That is, allow my trajectory to hop from higher excited state to lower excited state, or vice versa, by a stochastic algorithm. That is called fewest switch algorithm. I will not go into the theoretical formulation, but the basic idea is this. The schematic will look like this. So it is your initial molecular geometry R, and this V is your initial velocities. Okay, so you have this R0. You prepare Gaussian input, you prepare MolPro input, and ask MolPro, please give me energies, gradients, and non-adiabatic coupling. You can all do it very easily. I know everybody knows this. And then with these quantities, you calculate the probability of hopping between other states. If your trajectory hops to other electronic states, then okay. If it is not hop, okay, stay in the current state. And then go on. Next time, delta t. Again, next time, 2 delta t, 3 delta t, and so on. So the point is, at each trajectory, at each point, you send your nuclear coordinates to your quantum chemistry software, ask for this, and then calculate the hopping probabilities to decide whether you will stay on the same surface or hop down to the other surface. And you do much more, lot of trajectories. Finally, you will have this kind of picture that you have two surfaces, some of trajectory will remain in the same surface, some of the trajectories will hop down to other surface. So at the end of the day, at the end of your simulation, you have a probability of your molecule in the ground state, you have a probability of molecule in the excited states. That is we call web packet bifurcation. That is the goal of this non-adiabatic molecular dynamics simulation. Okay. Now, this is the basic idea of surface hopping simulations, but now I will show you few strategies for going long time scale. The first one is, at the end of the day, we are doing classical mechanics. We are propagating our trajectories by Newtonian equation of motion. And it does not have any nuclear quantum effects. What do I mean by nuclear quantum effects? What about zero-point energy? What about tunneling? The classical mechanics does not know anything about zero-point energy, right? Because we all know zero-point energy is a manifestation of quantum uncertainty principle. Okay, I have to take care of zero-point energy. Then these non-adiabatic coupling vectors. I did not show you the equations, but in the equation you will see this kind of vector, this kind of integrals. We call it non-adiabatic coupling vectors. It is the coupling between electronic states I and electronic states J. Those who are a little bit aware of non-adiabatic chemistry or those who are a little bit aware of computational chemistry knows how difficult and costly it is to compute. So I will show you energy-based, curvature-driven, approximated time derivative coupling where I will not require to calculate these integrals. And finally, of course, everybody is talking about this machine learning. I have these three strategies to tackle my simulation for long time scale. First, zero-point energy. As I am saying, that zero-point energy, your classical dynamics does not know anything about zero-point energy. You propagate your trajectories happily, but at some point during your propagation, you will see that some modes lose energy. And if you calculate the energy of your mode at that point, you may see that it goes below your zero-point energy value, which is not correct, right? You know that in quantum mechanics that you cannot be at an energy below your zero-point energy value. The problem is these leaking, actually the leakage energy is not flowing anywhere because you are in an isolated system. So this leaked energy actually accumulated to other modes, making it unrealistically hot. The quantum wave packet, this is not the situation if you propagate quantum wave packet, because quantum mechanics always knows where your zero-point energy value. It will never give you product below its zero-point energy value. But the same is not true for classical trajectories. To give you an example of zero-point energy value, in benzene you have ZPE of 50 kcal per mole. In adenine, 75. In pyrene, much bigger, 130 kcal per mole. What I'm trying to say is zero-point energy is a considerable amount of energy. And imagine a situation where the zero-point energy flows out of several modes and accumulates into only one single mode, specifically weak bond, let's say CH stretching. Then it will immediately dissociate. The hydrogen is immediately dissociates from the carbon. So the particular reaction channel can be artificially opened up or closed due to this erroneous energy transfer caused by your zero-point energy leakage. And of course, if you are talking about long time scale dynamics, zero-point energy leakage is severe. Okay, you have a simplet fix. You always have simplest thing, right? You ignored your 0 point energy in classical simulation. Then you have to discard a lot of 0 point energy violating trajectories who form products with less than their 0 point energy value. Bowman did that, but Bowman had to discard 85% of classical trajectories in a simulation of acetaldehyde, roaming reaction of acetaldehyde. Nowadays, I cannot afford such computational waste. So there are other methods called active methods, where we apply some constraint during the trajectory propagation. What are these constraints? These constraints are satisfying the 0 point energy threshold. They are monitoring that, okay, whenever 0 point energy is the energy is going below 0 point energy, my propagator is saying, no, it is wrong. Please go in some other path. So that is directly intervening the classical propagation of nuclei. And as you can see from the reference list, people, those are big names, already kind of engaged in this type of this type of correction. But all the previous corrections till now requires momenta of the normal modes. Why? Because, of course, what is 0 point energy? 0 point energy is the h nu, right? The half h nu. And what is half h nu? Nu is the normal mode frequency. So you will need Hessian calculation during all the propagation. And again, you know how much costly is a Hessian calculation is for a ab initio quantum chemistry method. I cannot afford it in my ab initio molecular dynamics. It will be very costly. So I want a Hessian free method, simple and general, that I can integrate with any classical propagator. And I present here our local pair 0 point energy correction. We do not require expensive Hessian calculation. The idea is very simple. We monitor the kinetic energy of local stretching vibration. At each point, I calculate the kinetic energy of the local stretching vibration. Whenever the kinetic energy drops below a certain threshold, that threshold actually is my 0 point energy value that I know beforehand. I pumped that leaked amount of energy in this particular pair. Of course, I add the energy ad hoc. So I have to compensate, right? So I have to take the energy, the extra added energy from the energy pool constructed by the other local pairs. So what I am doing, I am putting an extra amount of energy and subtracting that exact energy from the other bonds. So that is, energy is conserved inherently, keeping the system as a microcanonical ensemble. My total energy is always constant, as it should be. And all the corrections I am performing in the nuclear velocities only along the parallel direction. So now, as you can easily understand, it is a central force problem, right? So it inherently conserves the linear and angular momentum. Okay. So I applied this method in water dimer. So this is the water dimer case. If you do not do anything, if you not do anything, so as you can see here in this plot, left side plot, you are seeing the oxygen distance. So all the oxygen distance are exploding if you do not do anything, and your cluster is exploding, because the oxygen this vibration is actually accumulating energies from leaking CH stretching. And that is why it is now becoming extra hot and easily cross the dissociation energy. And that is why your cluster is here dissociating. But with this correction, I can maintain the cluster for a long period of time. Bowman did, this is the result from Bowman, the left side result from Bowman. So Bowman also did the exactly similar simulation, but with their method, and also can hold the dimer for a long time if he have this constrained trajectory propagation. But our method is now superior to Bowman method because he has to apply a very tiny time step compared to us. Now my time step is much bigger. That means my simulation is much faster. And Bowman did correct. Bowman applied his correction at every 0.24 femtosecond. I applied correction at every 10 femtosecond. That means I am less intervening the inherent dynamics. And the most important thing, I did not require Hessian calculation. So I published this method in 2022, and immediately 2024, Truller picked up this method. I'm talking about Don Truller from Minnesota University. Don Truller picked up this method and improved our method by putting kinetic energy redistribution. These two snapshots are from Truller's paper. Here the above one is ours. He called them Mukherjee-Barbati algorithm, where this is our pseudo protocol that we do a brute force energy conservation. But he here perform kinetic energy redistribution by putting a cost function and optimizing it. So they basically improved our method of local pair zero-point energy algorithm to correct zero-point energy leakage in classical trajectories in this year only. Okay. The next point is non-adiabatic coupling vectors. How to get rid of these non-adiabatic coupling vectors, because it is very difficult to compute. So actually, the mixed quantum classical dynamics never asks for the explicit non-adiabatic vector, Rather, it requires this integral. This is the coupling over time. Now, you can by a simple chain rule, you can prove that this actually corresponding to this non-adiabatic coupling vector dot product of nuclear velocities, R dot means velocities. So if I can approximate this quantity, then we do not require to calculate this integral, non-adiabatic coupling integral from ab initio quantum chemistry code. So our group, Barbati's group, and we developed a curvature-based approximated coupling. I do not want to go you details into the equation, but as you can see, this is a curvature-based approximation because here we need the time derivative of double time derivative of energy difference. So that is why it is taking care of the curvature of the potential energy surfaces. And again, Truller, so we published it in 2021, and again, Truller picked up this method and modified our method, and now he's saying that non-adiabatic dynamics without non-adiabatic coupling. So only potential energy and gradients are required. So he is now saying that RIP, non-adiabatic coupling. We do not require non-adiabatic coupling anymore. Okay, nice. And this is our results of a comparison of a benchmark of how the conventional non-adiabatic coupling vector and our improvised time-dependent Bacon coupling method works. So more or less, this is ethylene. You can see the population profiles. This is cyclobutanone. This is fulvene. So more or less, we are satisfied with the comparison with non-adiabatic coupling and without non-adiabatic coupling but approximated time derivative coupling. Last but not the least, machine learning, right? So the basic idea is we have to bypass completely the quantum chemistry calculation, because you all know quantum chemistry calculation is costly, is time consuming. You let's say you are doing benching, you prepare your input and say Gaussian calculate it, and you have to wait for at least 30 minutes if you do a DFT or TDFT, type of calculation to have simple energies and gradients, right? So if we only rely on quantum chemistry, then for 100 trajectories with 10 picosecond simulation, we need 2 into 10 to the power 6 single point ab initio calculations. Huge. Of course, it is accurate. No doubt on it, but expensive and slow. Rather, what if we calculate fewer number of ab initio calculation? Of course, we require reference point. We require quantum chemistry, but not huge amount. Only a small amount of quantum chemistry calculation, less than 10 to the power 4. And then we train a machine learning model. And then from this machine learning model, I ask, please give my energies and other quantities to propagate my trajectories. It will be very fast because now it is not solving any quantum chemistry codes. It is now analytical. So it will be very fast. And okay, we have to work on how good our machine learning model is, but more or less we can reach to qualitative accuracy. This is the basic schematic idea. So the protocol is, we have to generate training data set. Maybe you can generate from ab initio single point quantum chemistry calculations. You have to do a lot of single point quantam chemistry calculation and then prepare your machine learning model. Or you can even propagate some trajectories and then you collect snapshots because you hope that your trajectories will cover the phase space. And then you build your machine learning model. Basically, nowadays in market, we have kernel reduced regression model, neural networks, and even active learning. I will not go into detail, but as a spoiler, I can say you, neural networks are working much good. As you can see here, it is the solving dynamics. You are seeing the population, excited state population. In the dashed line, in the solid line, the population, the dynamics is carried out in a machine learned potential called MACE, message passing equivalence neural network. And the dashed line are derived from quantum chemistry, solving actual quantum chemistry. In this case, it is Casas-CF dynamics. So you can see within the error of margin, both the quantum chemistry and machine learning assisted dynamics are behaving exactly the same. But I want to raise 2 red flags here about machine learning chemistry. Accurate force is very essential in any kind of dynamics. Here I am showing you 4 different integrations setup. And I'm plotting the total energy deviation, right? Let's say about this, the orange one. Here, my integration time step is very small, 0.01. By the way, you cannot afford this small time step in your ab initio dynamics. You cannot simply afford it. But okay, for the model system, I am prepared it, and I let's say I do it. You see the total energy deviation is in the order of 10 to the power minus 7. It's a perfect. The world is perfect, right? But as I say, you cannot afford so tiny time step. So you increase the time step to 0.5. This is the violet. So again, the total energy deviation is 10 to the power minus 4 order. Okay, not bad, reasonable. Then I add a random fluctuation to my force in the order of 10 to the power minus 7. What you are getting? You are actually getting exactly the same like 0.5, 10 in the order of 10 to the power minus 4. That means your propagator, your dynamics propagator does not distinguish between the small random fluctuation in your force. Good thing. But then if I increase the random fluctuation in the order of 10 to the power minus 5, you will get complete garbage dynamics in the blues. So basically the point is, in your machine learning potential, you need to predict the force below in the order of 10 to the power minus 5, which is difficult, by the way. The second thing is learning excited states is very difficult because ground state there is a lot of well-defined electron densities, but in the excited states, electron densities are exotic. As you can see, these are all the root mean square error of machine learning between machine learning potential and quantum chemistry potential for S0, S1, S2, and S3 states of this molecule. This is okay, I think azindole molecule. As you can see, when I go up in the excited states, my errors are increasing. By the way, this plot is from 2022, but nowadays we are doing much better than this, but not yet to the mark. So here I conclude that I am trying to convince, I'm trying to say that, okay, fewest switch surface hopping could be a reasonably good method in the long time scale, because nobody knows that which method will work for the so long time scale. This is the first time I simulated this for long time scale and compared it. This paper will be in a submission process now. Okay. Then I showed you a 0-point energy leakage prevention protocol. And also there is a standalone Fortran module available in GitLab where you can just adopt this module and integrate it to your any classical propagator to prevent the 0-point energy leakage. By the way, we already did this for you. We have our Newton X software where I codified this correction scheme, so it is available now for you to use. And then I say machine learning assisted non-adiabatic molecular dynamics. Of course, it is promising. It is the future, but we have to proceed with caution. And finally, it's time for acknowledgement. I'd like to acknowledge Mario, where I did all my research in these 5 years, and now I am in Poland. So and the Center of Excellence, the reason of funding, the reason why I'm here. And thank you all for all your patience. And I would like to have any questions if you have any. Thank you very much.
Thank you, sir. Thank you for your informative session.
Am I well in time or?
You are within time, no problem.
Okay, I do not want to keep all the guests for so long from dinner. Now I know it is dinner time.
Okay, no problem. And this is very informative session actually, particularly for the students who are interested in the theoretical chemistry. So now it is time for the question and answer. If anyone want to ask question, please ask to Dr. Soikot. From the audience, please ask. No, so I have some queries. You are using the hopping mechanism.
Yes.
Where you uses the uh, purely Newtonian.
Could you please repeat? I cannot understand.
You are using hopping mechanism where you are
Yes.
using purely Newtonian mechanics, or there is a combination between the quantum mechanics and Newtonian mechanics.
Exactly. As I have shown you, the trajectories are propagated Newtonian mechanics. Okay, but for propagation, what we need? We need force.
Okay.
The force is actually derived by solving quantum chemistry. so that your trajectories are basically propagating on quantum chemical potential energy surfaces.
Okay, okay.
Yeah.
So, actually, here all your problems are purely quantum mechanical problems, right? Auto electronic transitions or that. So,
Yes.
these are the purely quantum mechanical phenomena, and using Newtonian mechanics in combined with classical mechanics. So you
No.
some results which is for the small molecules actually.
Yes. Yes.
Uh,
Because no, I can tell you this. Because I am a method developer, right? That is why we are using the small molecules. But these mixed quantum classical simulations work much better with big molecules. Because whenever you go large, that means your quantum effects are much prominent there.
yes, yes,
When right, so whenever you, so that is why when we do method development, we always use small molecules, because there the quantum effects are much bigger. So if I can predict the the quantum phenomena in the small molecule, you can be assured that it will be work very good in large molecules, because there the quantum phenomena are much less.
yeah. For the big molecule, there is non-adiabatic coupling are also large. So how
Uh,
you handle?
Yes, and that is why the non-adiabatic coupling laws. That is why there are a lot of state crossings are there.
Yes, yes,
You need to you will see a lot of internal conversion and inter-system crossing if you have a metal or something like that. But in this framework of quantum chemical approaches, you have those non-adiabatic coupling, right? and and what I showed you, you can approximate this non-adiabatic coupling by not calculate it explicitly,
okay, okay.
by these time dependent backend formalism, and it is working very good. And I am seeing people are using this for big molecules, for metal ligands. There is a group in Vienna, Leticia Gonzalez group. They are exactly doing surface hopping with big metal and ligands, and predicting very good results compared to experiments.
Okay, okay. Actually, one thing I want to know, you are doing dynamics on diabetic Hamiltonian or
No,
Dept?
we propagate on adiabatic Hamiltonian.
Okay, okay.
And that is why and people always ask that, okay, in adiabatic Hamiltonian you will have the singular non-adiabatic
Yes, yes,
coupling.
yes,
The answer is in your trajectories. Let's say you will propagating 100 trajectories,
yes, yes.
one or two trajectories actually hit the conical intersection. Other trajectories are not hitting, because you are propagating 100 trajectories. It is covering the entire phase space. But non-adiabatic transition is not happening exactly at the conical intersection. It can happen also around the conical intersection. So around the conical intersection, your trajectory is hopping down. But if by chance your trajectory exactly hitting the conical intersection, then your trajectory is then you have to throw that trajectories, because you will have numerical instabilities, as you know.
Okay. One more thing, just for query. So we need more number of trajectories to cover the whole the surface, right?
Exactly, exactly,
And there is
exactly.
also need much computation time.
Yeah, that is why people are now trying to save this via machine learning and everything.
Okay. Okay, nice. Shoykot Mukherjee, for your nice introduction and very informative session. Actually, this is for MA students. This is very good session. And if there is no further question, uh, I want to thank Dr. Shoykot Mukherjee uh, once more. Uh, Now we have reached the last part of today's international seminar. Uh, for the and the last part is the vote of thanks portion. I invite another convener of this seminar, Dr. Kriti Ranjan Sahu from the Department of Physics, Bhatter College, Dantan, uh, to give vote of thanks.
Thank to all present delegates and participants and the organization authority. Thanks to past author Professor Alok Anand Hajra, Vishwabharati University, West Bengal, India. He smoothly introduce us and explain what is green chemistry and explain the philosophy behind the green chemistry, what is it is importance in our daily life and protect our environment and society. And then thanks to the second speaker, Professor Subhash Banerjee, Guru Ghasidas University, Bilaspur, Chhattisgarh, India. He explained the green tools in organic synthesis. And thanks the third speaker, Professor Shoykot Mukherjee, Nicholas University, Poland, and explain the how the correlation with the green chemistry and how the time resolve the through their theoretical work. Uh, and the in the again thanks the key person Dr. Pijus Kanti Khatua, Principal Bhatter College, Dantan, and thanks the Dr. Subhankar Sardar, Department of Chemistry, Bhatter College, Dantan, the convener, and thanks the Dr. Alauddin Dafadar, Professor, Department of Mathematics, Bhatter College, Dantan, and also thanks the National Organizing Committee, Professor Sarajit Adhikari, Department of Chemistry, Indian Association for the Cultivation of Science, Jadavpur, Kolkata, and thanks the Professor Chittaranjan Sinha, Department of Chemistry, Jadavpur University, Kolkata, and also the Dean of the Science Faculty, Jadavpur University, and thanks the Dr. Biplab Sarkar, Chemistry Department, Northeast Hill University, Meghalaya, India, and thanks to the Dr. Amit Kumar Pal, Chemistry, Chemical Science Board Institute, India, and thanks Dr. Partho Roy, Central University of Rajasthan, India, and also thanks the local organizing committee, Monishankar Sahu, Department of Chemistry, Bhatter College, Mr. Professor Sutopat Chakraborty, Department of Chemistry, Bhatter College, and Professor Subhash Chandra Sen, Department of Physics, Bhatter College, and Professor Vishnu Priyajana, and the Department of Physics, Bhatter College, and Professor Tapos Kumar Chandra, Department of Physics, Bhatter College. Thanks to Sumo Das, Department of Physics, Bhatter College, Dantan, and thanks to Sumo Pradhan, Department of Mathematics, Bhatter College, and thanks Dr. Professor Shambhu Acharya, Department of Mathematics, Bhatter College, and again thank the three speakers. Um, One time calling them and they agree with our proposal, and again thank to all participants, about 61 participants present in various distribution, and also the thanks my professor Dr. Vikas Gulhare, my teacher also present here, and the
Thank you
thanks.
so much, Kriti.
Thank you. And also thank the college authority supporting to organize this type of conference, and welcome. Again, welcome. Next time we will arrange this type of conference. Again, welcome to participate, to enjoy our program. Uh, I request you say something our program. My teacher, Dr. Vikas Gulwari.
Thank you, Kriti, to invite me in this session. Overall, the program organized by your institute is too good and very informative, and just give the new information about the nature with the use of the green chemistry. How can we save the world? So overall, a lot of things we are using in a daily our life, and chemistry just be a part of it. So Sekat sir, Subhash sir, and Alaknanda sir, all professors gave the information about the green chemistry so good and very useful here. And just we have to think here the new dimension of the research. So as we think here in our daily life, so many things are continuously changing. So it is need to save the nature, and because we know very well, we cannot prohibit all those things we are using in our daily life. So that means a part of thinking just goes on here. So how can we save the it? So overall, the session is too good and very informative, and just hope that all the will and thank you all of and discuss terms of the today's program.
Thank you, sir. Mm, and every
Okay, welcome, Kriti.
anyone can collaborate with us for our further program. Always welcome from our three departments: physics, chemistry, and mathematics, as well as from our college authority.
Okay, I will just try because in our Bhatter Government College, chemistry is also there in PG department. So we will just try to collaborate with you, and in future we will try to organize this kind of the program. Okay, thank you.
Okay, thank you,
Okay.
sir. You are always welcome, sir. Okay. Thank you, Dr. Ranjan Sahu, for giving vote of thanks. I sincerely thank to all the participants to joining in this program because without participants, a seminar cannot be completed. On behalf of Bhatter College, Dantan, I wish to thank all the participants to their valuable time to this seminar. Thank you, and again thank you all again. With giving thanks to all, I wish to formally complete today's international seminar, Current Trends in Green Chemistry. And I have shared a feedback link in the chat box, and you all have to fill up it to get the formal certificate. Okay.
Okay, thank you, sir, so much.
Yes, sir. Thank you.
Can we leave, sir?
Yes, sir. You may.
Okay, okay, sir.
শুভঙ্কর,
হুম।
আমি বলছি ওই সার্টিফিকেটের জন্য লিঙ্কটা আজকেই দিয়ে দাও।
হ্যাঁ, আমি দিয়ে দিয়েছি সার্টিফিকেট লিঙ্কটা চ্যাট বক্সে। ওটা 3-4 দিনের মধ্যে সার্টিফিকেটগুলো দিয়ে দেবো।
হ্যাঁ হ্যাঁ, চ্যাট বক্সে বা আমাদের এই গ্রুপে দিয়ে দিল।
হ্যাঁ।
মানে 61 জন ছিলেন,
হুম হুম
61, 62